Good afternoon, everyone. First of all, I'd like to thank you all here today. My name is Ana Paula. I am a PhD student in chemical engineering at the State University of Maringá, and today I will present part of my research. It is entitled Rigorous Generalized Disjunctive Programming for the Design of Rainwater Drainage Networks. So let's start. Uh, Initially, sewage networks were designed to handle both wastewater and rainwater in a single system. And however, due to the challenging treatment in treating effluents, rainwater drainage networks and sewage collection networks were separated. And this separation is crucial because rainwater entering a sewage system can overwhelm sewage treatment, while sewage in the RDN, rainwater drainage networks, can harm the environment as each network serves different purpose. So the need for better sanitation, especially with the spread of diseases throughout history, pushed the development of these separate networks. As the computational technologies advanced, so did the engineering studies on these networks. So the rainwater drainage networks, they faces high flows and various unpredictability factors that is associated with extreme temporal events, natural phenomena, and climate change. Mm, Now, when it comes to optimization, meta-heuristic methods has been widely used in water and wastewater engineering. Techniques like ant colony optimization, particle swarm optimization, genetic algorithms, they're common, mentioned by various studies. Here's some references. And these methods are stochastic, meaning they often need special strategies like penalty functions and to handle the constraints. Most research has leaned towards stochastic methods because modeling equations can be complex. However, in this study, we propose a deterministic approach, which has a key advantage like precision, reliability, robustness, and reproducibility, all critical in engineering. So the goal of this work is to optimize the selection of pipe diameters and inclinations for RDN, aiming for minimal cost while ensuring velocity limits are respected, and all pipes stay within a maximum area occupation. To achieve this, we use a rigorous model for the design of rainwater drainage networks. Um, Here's the methodology that we used. So the rigorous model for RDN is presented as a generalized disjunctive programming problem, known as GDP, the acronym. And GDP is a high-level formulation that provides a theoretical framework designed to facilitate the modeling optimization problems with discrete and continuous variables through advanced logical construct, making model formulation more intuitive and systematic. And this model that we're going to present here today, this model is highly non-convex and non-linear because includes trigonometric functions, making it suitable only for small-scale problems. And the objective function, as we said before, is to minimize the cost pipe of the rainwater drainage network. The objective function is subject to a set of constraints. First, we have the continuity equation. So the left-hand side of the equation 2 represents the sum of all the flows entering node I, either from the exterior or from node J, which must be equal to the sum of flows going through node I to the node J, and plus the flow that leaves the network through node J. And equation 3 implies that the water will flow through the pipes until it reaches a sink node with a non-zero value, indicating that the ultimate nodes of the network will receive all the water. The nested disjunction in equation 4 indicates that if a pipe connecting nodes I and J is selected, which means that the Boolean variable Z it is true, then the hydraulic equations for that pipe must be solved. And furthermore, if a pipe is selected, it must be assigned one of the standard diameters and the corresponding cost must be calculated. And then the following bounds can be added to the model as maximum velocity allowed, maximum flow rate in connections IJ, the maximum wetted angle, maximum hydraulic radius, maximum wetted area, and the slope. And the equations 6 to 10, they are the equations that we use to calculate these hydraulic parameters. So we selected, a case study was selected to test the model as seen in figure 1. It is a fictional network. It is constructed with random but not unrealistic data and to test the functionality of the model. The basic requirements were that the network to be small, in other words, with a few nodes. So the solution involves ensuring the existence of a feasible network within the specific operating parameters, including maximum allowed velocities and slopes, as well as flow rates, and each pipe giving a water depth of 0.8. This ensures that the maximum velocity within the pipe is maintained, while also guaranteeing open channel flow. And this is the data, the parameters that we use to calculate the set of commercially available diameters and their cost per meter. And table 2, there are the test example design parameters like the maximum cover depth, minimum cover depth, and the many coefficients. These are the results for a case study that we used. So the model was developed in General Algebraic Modeling System as a GANS software, and we use K-neutral solver, and we find the maximum velocity established for the network flow was 4 meters per second. And K-neutral solver, he found an optimal solution amounting to 536.24 within 23.38 seconds of processing time. Well, the K-neutral solver, he proved to be more efficient in solving problems involving expensive functions, such as trigonometric and non-convex and non-linear functions, presented in this model, in this formulation. So as a conclusion, in this paper, we present an optimization model for designing rainwater drainage networks using standard pipe diameters. And the model was formulated as a generalized disjunctive programming and reformulated later as a mixed integer nonlinear programming. And this allows for a more rigorous design process and helps to determine the optimal operating conditions for the network. And the model itself, it's highly nonlinear and non-convex, which adds complexity, especially with the inclusion of trigonometric functions that some global solvers can't handle. However, using the K-neutral solver, we were able to solve the problem efficiently, and we found the optimal solution for this specific case that we studied. Thank you, everyone, for your attention, and I'll be open for questions. Thank you.